Right triangle word problem. A ramp with a 30-degree angle from the ground is to be built up to a 2-foot high platform. What will be the length of the ramp? How far from the platform will it extend to the nearest inch? With problems like these, it's very helpful to draw a picture. So we have a ramp that makes a 30-degree angle with the ground. So let's start with that. Here's the ground. Here's our 30-degree angle. And it's to be built up to a 2-foot high platform. So then here we have a platform and it's 2 feet high above the ground. So there's a right angle there, perpendicular to the ground. The first question is, what will be the length of the ramp? So this is what we're trying to find. Well, before I start to find x, I first want to fill in what this angle is. You might already know that since we have a 30-degree angle and a 90-degree angle, that this angle has to be 60 degrees. But if you didn't know that, you could find it because there are 180 degrees in a triangle. So if you add 30 to 90, you get 120. 180 minus 120 leaves you with 60 degrees for that third angle. Now that we know it's a 30, 60, 90 triangle, we can apply our 30, 60, 90 rules to finding the length of our ramp. Our ramp is across from the 90-degree angle, therefore that's our hypotenuse. The side we know, the leg we know, is across from the 30-degree angle, so it's our shorter leg. And the hypotenuse of a 30, 60, 90 triangle is twice as long as the shorter leg. Our hypotenuse, again, we're using x for, equals 2 times the shorter leg, which is that 2-foot side. So 2 times 2 feet, which means x is 4 feet. Therefore, the length of the ramp is 4 feet. So we've answered the first question. Then they asked, how far from the platform will it extend? How far from the platform will the ramp extend? So now they're asking us to find that length. And y is across from our 60-degree angle, so that's our longer leg. And the longer leg of a 30, 60, 90 triangle is the square root of 3 times the shorter leg. Our longer leg, again, is y, equals the square root of 3 times, and our shorter leg is still that 2-foot length. So y is 2 square roots of 3 feet. They didn't ask us for the answer in feet, they asked to the nearest inch. So the first thing I'm going to do is convert 2 square roots of 3 feet into inches by multiplying by 12. So y is 2 square roots of 3 times 12, since there are 12 inches in 1 foot, which is 24 square roots of 3 inches. But they didn't ask for it in simplest radical form, so then we'd actually want to calculate what 24 square roots of 3 inches is, and it's about 42 inches. Therefore, how far from the platform will the ramp extend? The ramp will extend about 42 inches from the platform. There we have it. Absolute value. Absolute value is the distance of a number from 0 and is always positive. It's denoted by a pair of vertical lines surrounding the value, such as the absolute value of 3. You can think of absolute value like you're being asked a question. And the question is, how far is 3 from 0? 3 is 1, to 3 places from 0. So the absolute value of 3 is 3. The absolute value of a negative number and its positive counterpart are the same. So the absolute value of negative 3 is also 3 because negative 3 is also 3 places from 0. 1, 2, 3 places from 0. The absolute value of a difference, when you're doing that, the order doesn't matter. Let's look at the absolute value of a couple of differences. The absolute value of 8 minus 3 and the absolute value of 3 minus 8. When you're doing the absolute value of a difference, again, the order doesn't matter. The result will still be the same. Let's see how that happens. Start on the inside finding your difference. 8 minus 3 is 5. So we have the absolute value of 5. And again, absolute value is the distance from 0. 5 is 5 places from 0. Now we'll look at the difference switched around. 3 minus 8. 3 minus 8, you could do add the inverse, so 3 plus a negative 8. 3 plus a negative 8 is negative 5, so we have the absolute value of negative 5. And like we talked about over here, the absolute value of a number and its negative counterpart are the same. So the absolute value of 5 and negative 5 is the same because, again, absolute value is the distance from 0, and distance can never be negative. So the absolute value of negative 5 is also 5, since negative 5 is 5 places from 0. Domain and range. State the domain and range of the function y equals x squared plus 5. In order to do this, we first need to understand what a domain and a range is. The domain of a function is all the possible values that could be plugged in for x. Any number that could be plugged in for x. So the domain is the set of all permissible inputs. Inputs, again, being x values, the numbers that can be plugged in for x. So it's any number that can be plugged in for x. And the domain is the whole set of those numbers. The range, then, is once those numbers are plugged in, what are the values for y? Because the range is the whole set of y values. So it's the set of all possible outputs. Output being y value. Now that we understand what these words mean, we can answer this question. So the domain, again, is the set of all permissible inputs. So basically, which numbers can be plugged in for x? So looking at our function, what numbers could we plug in for x? Really, any real number. Positive, negative, a square root number. Anything we wanted to plug in would work in this function. So our domain, then, is all real numbers. Now for the range. Again, the range is the set of all the possible outputs or y values once we've plugged in our domain or our set of inputs. So since our x is squared, that means that our answer is always going to be a positive number. We can never get a negative number since we're squaring x. Even negative 4 squared would be a positive 16. So the lowest this x squared could possibly be would be 0, because 0 squared would give you 0. But then with this plus 5, That now means that the lowest value that y will ever be is a positive 5. So your range would be all real numbers greater than or equal to 5, since 5 is the lowest it can go. 5 would be the lowest value, but then of course it could be anything above 5. So there's the domain and the range. Graphing solutions to linear inequalities. First, we're going to graph y is greater than 1/3 x plus 2. To graph a linear inequality, we're going to graph the line as if this were an equal sign, and then if it's greater than or less than, it's a dashed line. If it's greater than or equal to, less than or equal to, we use a solid line. So since this is just greater than, we need to use a dashed line. This is in slope-intercept form. Y equals mx plus b. So our slope is 1/3. And our y-intercept is 2. So we're going to start with our y-intercept at 2, and then use our slope to find our next point. Rise 1, run 1, 2, 3. And then we'll draw our dashed line. Connecting our 2 points. The final thing we need to do to graph an inequality is to shade. But where do we shade? One way to figure this out is to pick a point on either side of the line and see if it satisfies your inequality. If it does, then that's the side you shade. If it doesn't, then you shade the opposite side. A good point to use is 0, 0 because it's pretty easy to solve for. So y is 0. Is 0 greater than, and then again we'd plug in 0 for x, 1/3 times 0 is 0, 0 plus 2 is 2. So is 0 greater than 2? No, it isn't. Which means since 0, 0 does not work, it is not a solution, then this is not the side we shade. So we shade the other side. And really everything above this would be shaded, but I'm not going to color the whole board. So this would be your solution to this inequality. Every point in this shaded region would make this inequality true. However, points on the line would not make the inequality true, since its y is greater than, not greater than, or equal to. And that's why this line is dashed, to symbolize that the points that are on this line, the points that lie on this line, do not satisfy this inequality. Now we're going to graph a system of inequalities. The same rules apply, but where you shade is a little bit different. So first we're going to graph y is greater than or equal to 2x plus 3. Since it's greater than or equal to, we use a solid line. And again, it's in slope-intercept form. So our slope here is 2, or 2 over 1, and our y-intercept is 3. So we start with 3, up 1, 2, 3. And then we use our slope, rise 2, run 1. Now we can draw our solid line through these points, because again it's a greater than or equal to. And there are a couple of different ways you can do the shading. One thing you could do is start by figuring out where you would shade for this line. So like again, you could use that point 0, 0. 2 times 0 is 0, 0 plus 3 is 3. Is 0 greater than or equal to 3? No, it isn't. So for this line, we'd be shading on this side of the line. And we can put it like a little dot here just to remind ourselves. This is the side we'd be shading for this line. And then you can graph your other line and see where you'd shade for that one. Where they overlap is going to be the solution. And that's one way, and I'll show you another way when we're done graphing the other line. So this next line is y is less than negative 1/2 x minus 2. Less than, since it's not less than or equal to, that means we're going to be using a dashed line again. And again, it's in slope-intercept form, so our slope is negative 1/2 and our y-intercept is negative 2. So start with the y-intercept, negative 2, and then use your slope to find your next point. Rise 1, or actually we're going down 1 since it's a negative 1, and then over 2. And again, this is a dashed line because it's just less than, not less than or equal to. We're going to connect our points with our dashed line. And put our arrows on the end to signify that that line goes on. So now that we have our two lines crossing, we've actually created 4 regions. We have this region, this one, and this one. For our first line, this region was what was shaded. So now we need to see where we're shading for our next line. Is it above the line or below this dashed line? Again, I'm just going to use 0, 0 in order to check. So negative 1/2 times 0 is 0. 0 minus 2 is negative 2. So is 0 less than negative 2? It is not. So this is not where we're shading for this one. We're shading down here in this region. And so where the two shaded areas overlap would be right over here. This is your solution, since for this line we were shading on this side, and for this line we were shading on this side. So the two shaded areas that overlap is just this region right here. And another way you could figure this out is just to pick a point in all 4 of the regions. And if the point satisfies both equations, then that's where you shade. And if your point doesn't satisfy both equations, then we don't shade in that region. Graphing the inverse of a function. The inverse of a function is the same as the original function, but with the independent and dependent variables switched, which just means switch the x and y values in the coordinates. The inverse of a function and the original will look the same, except that again, those x and y values will be switched, which means that they will be symmetric, the two graphs will be symmetric about the line y equals x. Let's look at an example. Graph y equals 2x plus 3 and the inverse. Y equals 2x plus 3 is a linear equation, and it's in slope-intercept form. Y equals mx plus b. The m is our slope, so our slope is 2, or 2 over 1. And our y-intercept is 3. B is 3. To graph a linear equation, we start by graphing the y-intercept. So on our y-axis, we go up to 3, and there's the first point for our line. The slope is our rise and our run. So we need to rise 2 and run 1 from that point. Rise 2, run 1. Now we just need to connect those points with a line. and then put arrows on the end of our line to signify that that line goes on forever. So that's the graph of our original function, but how about the inverse? Remember from just a minute ago that the inverse of a function is just where the independent and dependent variables are switched. The independent variable being the x and the dependent being the y. So one way we could graph our inverse function is just to take our x and y coordinates from each one of these points and switch them. So this ordered pair is 0, 3, which means that our inverse function will have the ordered pair 3, 0. Just switch the x and y. So over 3 and then up 0. There's the first point for our inverse function. Then we can take this other point we put on our graph, which is 1, 5, and do the same thing. Just switch the x and y coordinates, which makes it 5, 1. So over 5 and up 1. We could have done this with any 2 points from our original function, but since these were the 2 points we used to graph our line, they were easy to use to switch the x and y coordinates. Now that we have our 2 points for our inverse function, we can connect those with a line. And put arrows on the end to signify that it goes on and on and on forever. Now that's one way to graph an inverse function, to graph the original and then take the ordered pairs from the original and switch them. The other way to graph an inverse function, or another way to graph an inverse function, is to take the original function and again switch the x and y. So the y becomes x and the x becomes y. Now if we wanted to graph this, we'd want to put it in a form like slope-intercept form, which means we must solve for y now. So start by subtracting 3 from both sides. X minus 3 is equal to 2y, plus 3 minus 3 are additive inverses, so they cancel. And then we divide both sides by 2 to solve for y. 2 divided by 2 is 1, and 1 times y is y. I'm going to use the symmetric property to flip this around, so I get y equals x minus 3 divided by 2. Or y equals x divided by 2 minus 3 halves, or y equals 1/2 x minus 3 halves. You can write it in lots of different ways. But then you could graph this inverse function the same way we graphed our original function by graphing the y-intercept, -1.5, and mine's a little off because of human error, but it should be about right there. And then we would use our slope 1/2 to rise 1 and run 2. So when you're graphing a function and its inverse, just remember, switch the x and y. Graphs of functions. The first graph is a linear function. It graphs a line. The second graph is what's called a quadratic function. Quadratic functions graph a u or a parabola. The third graph is an exponential function. Exponential functions start out increasing very slowly and then start increasing more and more rapidly. This next graph is the graph of a logarithmic function. A logarithmic function is the inverse of an exponential function. We should also talk about the asymptotes of an exponential and a logarithmic function. An exponential function has a horizontal asymptote of y equals 0. While a logarithmic function, since it's the inverse of an exponential function, has a vertical asymptote of x equals 0. And an asymptote is just a line that the graph is approaching but doesn't cross. The next graph is what's called an absolute value function. And it graphs a V. It looks like a V. So they're straight lines, and then the left side is just the reflection of the right side. This next graph is the graph of a square root function. And a square root function is a parabola turned on its side, and it's just the top half of the parabola turned on its side. And then the last function is the graph, this is the graph of a rational function. And rational functions have two branches, one in the first quadrant and one in the third quadrant. If you look at this branch here, as we move from left to right, it's decreasing. And the same with the other branch, as we move from left to right, it decreases. And so there are some of the basic functions and their graphs. Linear equations. Marielle has 10 coins in her pocket. All of them are quarters and dimes, and their total value is $1.60. How many of each type of coin does she have? We can solve this by using a system of equations. We're told that she has 10 coins in her pocket and that they're all quarters and dimes. So if we use D for the number of dimes and Q for the number of quarters, then one of our equations could be her number of dimes plus her number of quarters is 10 total coins. Next, we're told that the total value is $1.60. Well, dimes are worth 10 cents. So 10 times however many dimes she has, plus quarters are worth 25 cents, so 25 times however many quarters she has will give us a total of 160. We've eliminated the decimals, so we just move the decimal over 2 times to the right for all of our numbers. So instead of 10 cents, we have 10. Instead of 25 cents, we have 25. And instead of $1.60, we have 160. But you could leave the decimals in there if you wanted to. Now to solve this system, we've got 3 options. We could graph both of these and see where they intersect. We could use substitution or elimination. And it's your choice. For this particular problem, I'm going to use substitution. So I'm going to solve for D in my first equation so I can substitute it in my second equation. So D is equal to, and I have to subtract Q from both sides, so negative Q plus 10. To solve for D, subtract Q from both sides, and you get negative Q plus 10. So in my second equation, I'm going to use negative Q plus 10 to substitute for D. So we have 10 times the quantity instead of D, negative Q plus 10, plus 25Q is equal to 160. Now we can solve for Q. To do that, first we need to distribute. 10 times negative Q is negative 10Q. 10 times 10 is 100, so plus 100, plus 25Q equals 160. Now to solve for Q, we need to combine like terms. Negative 10q plus 25q is 15q. Plus 100 is equal to 160. Subtract 100 from both sides. And we get that 15q is equal to 60. Now we divide both sides by 15. 15 divided by 15 is 1, and 1 times q is just q. We get that q is 4, which means she has 4 quarters. So how many dimes does she have? Well, we know that her number of dimes is equal to negative q, so negative 4, plus 10. So her number of dimes is negative 4 plus 10, 6. So we can say Marielle has 4 quarters and 6 dimes in her pocket.
In math, we have rational numbers and we have irrational numbers. So we're going to be taking a look at rational numbers, which have 4 different categories, and those are integers, percents, fractions, and decimals. So we're going to define each of these. Even if you're already somewhat familiar with them, we're going to go ahead and define them and give some examples. So starting out with integers, integer is a positive or negative whole number or 0. So 9 would be a whole number. It would be an integer because it's a positive whole number. Negative 6 is an integer because it's a negative whole number. Then of course 0 is an integer because we said it was. And so now we move on to percents, which is kind of a more complicated way to say percent is a part per 100. So an example of a percent is 20%, which we could also write as 20 parts per 100. But the important thing here is just you know what a percent is, like 20%. Then fractions, which is a proportion. So an example would be 20 divided by 10 or 2 divided by 4. And of course we have decimals, so this is where we have an integer, maybe 1, maybe 89, maybe 0. And then we have a decimal place, and then we have numbers after the decimal, like 20.53. So we have our integer, we have a decimal, and then we have numbers after the decimal. So integers, percents, fractions, and decimals are all rational numbers, usually. There are some rules. So in order to be a rational number, just summarize, it either has to be an integer, like we talked about. If it's a number like 9, negative 6, 0, it's always going to be a rational number. It gets more complicated when we come to fractions and decimals. If it's a fraction, it has to be an integer divided by an integer. And this integer cannot equal 0. So it's an integer divided by an integer. So 7 divided by 4 cuts it. That works. Now, decimals are a little bit more complicated because it either has to be a terminating decimal or a repeating decimal. So an example of a terminating decimal would be something like 2 divided by 4. From that you get 0.5. It ends right there at the 5. Or a repeating decimal, you do 1 divided by 3 and you get 0.3333. It goes on forever. But notice we're getting the same number every time. So really you could erase all of these 3's and just put a line over the 3 showing it's a repeating decimal. What you don't want is a decimal like pi, where you have 3.1415926. 5359. It just keeps going on and on. So there's no ending to it, so it's not a terminating decimal, and there's no pattern to it, so it's not a repeating decimal. That's what an irrational number is, one that just keeps going like this. These numbers, they have basically a stopping point. And so that's what we're looking for. And so The reason I say that a fraction has to be an integer over an integer is because when you divide an integer by an integer, you get a clean number. You get a decimal that's repeating or terminating. When you start dividing a decimal or a fraction by a number or a fraction by another fraction, that's when you're going to start getting messy. So really, if you're wondering whether a fraction is a rational number, what you can do is go ahead and divide it out and then look at the decimal and decide whether it's terminating, repeating, or non-ending. And that's how you can determine if it was a rational number.
Solving a quadratic inequality. Solve x squared minus 3x minus 10 is greater than 0. One way we could solve this inequality is to graph it. And then, since it's a greater than sign and not or equal to, we would graph a dashed line, and greater than means to shade above the parabola. And so the solution set would be all those coordinates in the shaded region. If this were a less than sign, then we'd simply shade below the parabola, and all the coordinates, again, in the shaded region would be the solution. The other way to solve is to factor, and that's the way we're going to do it here. So I'm going to factor x squared minus 3x minus 10, and I'm going to solve it as an equation first. So I'm going to change our greater than to an equal sign. So I know this is an x and an x, so that when I FOIL, I get my x squared. And I need two numbers that have a product of negative 10 and a sum of negative 3. So those numbers that have a product of negative 10 and a sum of negative 3 would be negative 5 and positive 2. Negative 5 times 2 is negative 10, and negative 5 plus 2 is negative 3. And now we'll use the zero product property to solve. X minus 5 equals 0. X plus 2 equals 0. Add 5 to both sides. So x equals 5. Subtract 2 from both sides. And x equals negative 2. Now our solution set is either the set of numbers that's between these two numbers, or it's the set of numbers that's outside these two numbers. So if it's between negative 2 and 5, we'll just pick a number and we'll see if it works. And an easy number to pick between negative 2 and 5 is 0. And if 0 does not satisfy our inequality, then our solution is not the set of numbers between these, but instead it's the set outside. So we're going to try 0, because that's a number between negative 2 and 5. 0 squared is 0. Minus 3 times 0. 3 times 0 is 0. So 0 minus 0 minus 10, that's negative 10, is greater than 0. That's not a true statement. Negative 10 is not greater than 0. So our solution set is not the set of numbers between these numbers, but instead it's the set of numbers outside. So x is less than negative 2, or x is greater than 5. And those values, if you pick a number, say 10. 10 squared is 100. 100 minus 30 is 70. Minus 10 is 60, and 60 is greater than 0. And see, that's a number that's greater than 5, and that number works. And then if you tried another number back here, a number that's less than negative 2, say negative 5 or even negative 10, negative 10 squared is 100. Negative 3 times negative 10 is 30. So 100 and plus 30 is 130, minus 10 is 120, and 120 is also greater than 0. So you can see that the set outside these numbers, numbers that are less than negative 2 and numbers that are greater than 5, do satisfy our inequality, while the numbers between negative 2 and 5 did not, like 0. Solving problems with quadratic equations. A swimming pool is 11 feet longer than it is wide. The area of the pool is 276 square feet. What are the dimensions of the pool? Dimensions being our length and our width. So what they're asking us to find are the length and the width of the pool. They gave us some clues that we can use. First one is that the pool is 11 feet longer than it is wide. So if we said the width was x, then the length would be the width plus 11. Now to find the area of a rectangle, the area is length times width. And they told us the area. And we have expressions for our length and our width, so we're just going to substitute. The area is 276 square feet is equal to the length, which is x plus 11, times the width. So x times the quantity, x plus 11. And then we can simplify by distributing. So 276 is equal to x times x is x squared, and x times 11 is 11x. This might look a little familiar to you. If we subtract this 276 from both sides, then we get our standard quadratic equation. 0 equals x squared plus 11x minus 276. And now that we have that, we can factor it to find what x is. So 0 equals x and x, because when we FOIL, x times x gives us x squared. Now we need to find two numbers that have a product of negative 276 and a sum of 11. So that would be positive 23 and negative 12. 23 times negative 12 is negative 276, and 23 minus 12 is 11, or plus a negative 12 is 11. Now we can use the zero product property to solve for x. So x plus 23 equals 0, and x minus 12 equals 0. To solve for x here, we subtract 23 from both sides, and x equals negative 23. To solve for x here, we add 12 to both sides, and x equals 12. Now if you'll remember, x was our width. And it doesn't make sense for our width to be negative, so this answers out. Which means our width is 12 feet. So width equals 12 feet. And if our width is 12 feet and our length is 11 feet longer than that, then 12 plus 11 is 23. So the length is 23 feet. And there are dimensions of the swimming pool. And we can check that by multiplying 23 times 12, and you will in fact get 276 square feet. So that means that we solved it correctly. Square root and perfect square. The square root of a number is the reverse of squaring a number or raising a number to the second power. The square root is the number that when multiplied by itself equals that value. For instance, the square root of 4 is 2, because 2 times itself is 4. 4 is a perfect square. A perfect square is a value that has a whole number square root. The square root of 4 is 2. So its square root is a whole number, which means that 4 is a perfect square. Another example of a perfect square is 9. The square root of 9 is 3. So the square root is a whole number, which means that 9 is a perfect square. The square root of 3 is not a perfect square because the square root of 3 is not a whole number. The square root of 3 is actually an irrational number. You can find the value on your calculator, but it does go on forever and ever. Roots can be expressed in exponential form as fractions. So the square root of 3 we could write is 3 to the 1/2 power. These are equivalent. You could write the cube root of 8 also as a fraction, as an exponent with a fraction. So that'd be 8 to the 1/3 power. And the cube root of 8, it's very similar to finding the square root of a number, but when you find the cube root, you're finding what number times itself 3 times gives you 8. So the cube root of 8 is 2, because 2 times 2 times 2 is 8. Some roots have coefficients, like 4 square roots of 7. And the coefficient is the number in front of the radical. And if there isn't a coefficient shown, like with these numbers, the square root of 4, square root of 9, square root of 3, or the cube root of 8, then it's understood to be 1, since 1 times any number is itself. But this coefficient is just a number that's multiplied by the radical, like 4 times the square root of 7. And it's written without any multiplication sign. It's just understood that this is 4 times the square root of 7.
The general equation for a circle is the quantity of x minus h squared plus the quantity of y minus k squared equals r squared. So here, h and k are the coordinates for the center of the circle on a coordinate plane. And then r is the radius of the circle. Now, we have something called unit circle, which has a radius of 1, and the center is at the origin. And the origin is where the x-axis meets the y-axis, which is right there, and the center of the coordinate plane. And so the coordinates for the origin is 0, 0, because it's at point 0 on the x-axis and point 0 on the y-axis. And so if we were to plug the numbers 0 and 0 into into h and k, then we would be able to simplify this equation. And then also the radius is 1, so we can plug that in to r right there. So we can go ahead and simplify this equation to get this right here, because since h and k are 0, we can take those out of the way, and then we just plug 1 into r, we square it, and we still have 1. So this is the equation for a unit circle. Now, we have something called standard position, which is the position of an angle of measure, blank, whose vertex is at the origin. So right here, you see this angle, and so I'm just going to label it with the angle symbol. We don't know what the angle is. But the vertex right here is at the origin of this coordinate plane. And then the initial side crosses the unit circle at the point 1, 0. So this right here is the initial side, and it meets the circle right there, crossing the circle at point 1, 0. Now the initial side is always going to cross the circle at point 1, 0. And the reason that it's always going to cross it at point 1, 0 is because the initial side always has to be on the x-axis of the coordinate plane. And so in order to do that, it must be on the y-axis at point 0. And then the terminal side, which is the other side, this side right here, this is the terminal side, it crosses the unit circle at some other point. And so we label that point AB. So it meets it right there, and we label that AB. Now there's a few things we can conclude from this setup. The sine of the angle measure equals B. The cosine of the angle measure equals A. And then the tangent of the angle measure equals B divided by A. So those are a few things to keep in mind. And so this is a look at unit circles and standard position.